Today we're going to look at two very famous integrals. These are called the Fresnel integrals, and they're classically found in a complex analysis type course. And in fact, you would evaluate these integrals using contour integration. But today we're going to follow a strategy which was employed in this nice paper by Hongwei Chen, the Fresnel integrals revisited, that calculates their value without using contour integration. So I think that's pretty nice. In fact, we're going to employ something involving differential equations. So let's just recall what the Fresnel integrals are. So the first one is the integral from 0 to infinity of cosine x squared dx. And the second is the integral from 0 to infinity of sine x squared dx. For the purposes of this video, I'll say that this first one, the cosine one, is lowercase a, while as the sine one is lowercase b. Okay, so now let's get going. So we're going to look at a parameterized family of integrals for which these are a special case of that parameterized family. And I'll call those capital A, T, U. So in other words, this is like a function of T and U, if you will. And here we'll have the integral from 0 to infinity of e to the minus t times x squared, and then cosine of u times x squared dx. And then likewise, we'll have b evaluated at tu will be defined similarly. So we'll have the integral from 0 up to infinity of e to the minus tx squared, and then sine of ux squared dx. And now let's notice that if we take a, and if we evaluate it at t equals 0, it's not exactly t equals 0, it's really a limit as t is approaching 0 from above, so I'll maybe put a little plus there. And then we evaluate it at u equals 1, we get the first of our Fresnel integrals, lowercase a. And similarly, if we do that to our parameterized family B, we get our lowercase b, which is the sine Fresnel integral. Okay, so now, like I said, we're going to use strategies involving differential equations, which means we need to think of these, this capital A, T, U, and this capital B, T, U, as functions, and build a system of differential equations involving these functions. Okay, so let's do it. Let's first take the partial derivative of a with respect to u, and let's notice that is negative the integral from 0 to infinity of x squared times e to the minus tx squared times sine of ux squared dx. And of course, we've used the trick of exchanging the order of integration and differentiation, but that's okay in this case. And really, how did we get this? Well, we got this from the chain rule. When we take the derivative of this cosine ux squared with respect to u, the x squared pops out, and then the derivative of cosine is negative sine. So that's why we have something like this. Okay, and then likewise, we can take the partial of b with respect to u and get something fairly similar. Here we'll have the integral from 0 to infinity of x squared e to the minus tx squared, and then cosine of ux squared dx. So already we can kind of see where we're going. This partial with respect to a of u looks a bit like our capital B function. It's not quite that exactly because we've got this x squared here, but it's in the same family. And likewise for the partial of b with respect to u. Okay, so next up we're going to use integration by parts on the partial of a with respect to u formula. And this will be integration with respect to u. So I'm going to use this DI method, which can be generalized to something like this fairly easily. So let's make our chart. We'll have our D column and our I column. Okay, so for the I column, we need something that we can take the antiderivative of fairly easily. And in this case, I think a good choice will be x times e to the minus t x squared. Okay, so of course, like, we'd have to do some sort of substitution to take the antiderivative of that, but since this is a pretty complicated problem in the first place, we'll gloss over those details. Okay, so left over would be something like this. We'll have x and then sine of ux squared. Great. And now notice I haven't taken into account the minus sign. I'll just have that be out front in the end. Okay, so now let's take derivatives down the left-hand column and antiderivatives down the right-hand column. So taking derivatives of this with respect to x, recall that we want to do everything with respect to x because we're integrating with respect to x. That will give us sine of u times x squared. And then taking the derivative of the sine portion with respect to x will give us plus 2x squared u times cosine of ux squared. Okay, so anyway, that's what we get for this derivative. Then taking the antiderivative down that I column will give us minus 1 over 2t e to the minus tx squared. Okay, so that sets up our integration by parts, and now we'll do our matching. So we'll attach this to a plus sign, this to a minus sign. We'll match across this diagonal. And then since we're truncating this, we'll match these straight across, but put them inside of an integral. All right, so now let's apply our integration by parts formula for this partial of a with respect to x, keeping in mind that we're doing the integral with respect to x. I'm gonna also introduce some simplifying notation of this partial of a with respect to u is a prime. So that might be a bit confusing because there are x's floating around here, but I think that if we are careful to remember this, it should be okay. Okay, so I'll have my a prime is equal to, so I'll have my matching on the diagonal right here, evaluated from 0 to infinity. But let's be careful because there's a minus sign out in front of this whole thing. So minus in front of the whole thing, put the whole thing in brackets like this. Then, like I said, now we will have minus x over 2t, and then e to the minus tx squared sine of ux squared, evaluated from 0 up to infinity. So that's what's happening on this diagonal. And then we'll have the integral of the product of these two objects. Notice both is attached to a minus sign, so that minus sign will cancel. Furthermore, we can take this 1 over 2t out, giving us plus 1 over 2t. Then we'll have the integral from 0 up to infinity of, let's see, we've got an e to the minus tx squared term, which we can factor out of the whole thing. And then we'll have sine of ux squared from this term. And then plus 2 times u times x squared, so 2ux squared times cosine of ux squared from this other term, and then dx, and that's all within this big bracket. Okay, nice. Now we're ready to take care of this evaluation term. Notice if we evaluate this at 0, we get 0. That's because the sine of 0 is 0, and also evaluating this term right here also gives us 0. And then as x approaches infinity, this whole thing will approach 0 because we've got this exponential decay term. Keeping in mind that our t values will be positive here. I didn't point that out, but we should be careful to remember that our t values are positive. Okay, so that means all of this just becomes 0. Okay, but notice we've got some things that look pretty nice now. Notice if we were to take the product of e to the minus tx squared and this sine term right here, we would get exactly our capital B integral. I'll call this capital B. I won't say of t and u, just to simplify it. And then likewise, if we take this e to the minus t squared and multiply it through to this, we don't exactly get the derivative of b like we have right here, but we get something fairly close. We'll get a multiple of the derivative of b. Okay, so let's write all of this down in the end. So we'll have a prime is equal to negative 1 over 2t, the minus sign comes from this, times b, that's this b right here. And then we'll have minus u over t. So these 2's cancel, and we'll have the u over t, and then b prime. The x squared cosine ux connected to the exponential is our b prime. Okay, good. So here is one differential equation that fuses a and b together, and you can do essentially the same thing with integration by parts on b prime to see that b prime is in fact equal to, let's see, it'll be 1 over 2 times t a plus u over t times a prime. So we've got this nice system of differential equations for capital A and capital B. So here's this nice system of differential equations that we had on the last board. Now I'm going to start by clearing denominators here. So I'll multiply the whole thing by, let's see, maybe 2 times t to clear denominators. So let's say this yellow arrow means I'm going to multiply everything there by 2 times t. That'll give me 2t a prime equals negative b, and then minus 2 times u b prime. And then likewise, I'll have 2 times t b prime equals capital A, and then plus 2 times u a prime. Okay, good. And then next up, I'm going to take this first equation, leave it as is, and then multiply this second equation by I and add them together. So like I said, I'm going to multiply this by I and then add. And let's see what that leaves us with. We'll have 2t and then a prime plus I times b prime. That's what we get over here on the left-hand side of the equation. And then we'll have I times a minus b. That's what we get for these two terms right here. And then plus 2 times u, I times a prime minus b prime. And now from here we're going to do a nice little trick where I take this negative b and rewrite it as plus I squared times b. So in other words, we'll have I times a plus I squared times b here. Then we'll do essentially the same thing here, but with derivatives. So I'll have I times a prime plus I squared times b prime. And that motivates the ability to factor an I out of each of these terms. That leaves us with I times a plus I times b, and then plus 2u times I, and then a plus ib. Sorry, that should be a prime plus ib prime. But now let's notice that we've got a plus I times b everywhere, which motivates the following definition or the following introduction of some simplification. And that will be z equals a plus I times b. That's also motivated like over here by that sort of combination of cosines and sines giving us the complex exponential. So that's like motivated for a couple of different reasons. Okay, so now we can rewrite this definition or this differential equation as follows. So we'll have 2 times t times z prime, that's what happens on this left-hand side, equals I times z plus 2 times u times I times z prime. But this is a nicely separable differential equation. Notice that we can maybe move all of this stuff over, and we'll have 2t minus I times u times z prime. So just to reiterate, that's from moving this term to the left-hand side of the equation and factoring everything out as appropriate, equals I times z, which tells us that z prime over z is in fact equal to I over 2. So that's what we get, I over 2, and then 1 over t minus I times u. But now I'm going to do one more thing before we start solving that differential equation, and that is multiply the numerator as well as the denominator by I here. So this I times I here will give us -1, and then distributing this I through here will give us I times t plus u. So we'll have z prime over z is equal to minus half times 1 over u plus I times t. Great, and that's a nice differential equation. Okay, so let's bring that up to the top and we'll keep going. All right, so now we've got the following differential equation, which is, like I said, a separable differential equation. Before moving on any further though, I want to make an initial condition here, and that will be the initial condition where u is equal to 0. Let's recall that by primes here we mean derivatives with respect to u. U is the variable of this differential equation. T is simply a parameter. So if we stick u equals 0 into z, recall that z is a plus bi, well, this part is going to totally disappear because sine of 0 is 0. And then this part right here will give us one of the Gaussian integrals. It will be the integral from 0 to infinity of e to the minus tx squared dx. I won't work out that value. I think we've done that on the channel before. But what we end up with is 1 over 2 times the square root of pi over t. Maybe we could rewrite that as the square root of pi over 4t. That would be a nice way to write it, like all in one piece. So there's our initial condition. So now let's take the antiderivative of both sides of this to work towards a closed form for z. Okay, nice. So we'll first have the natural log of z equals minus 1/2 times the natural log of u plus I times t plus our constant c. But let's notice we can bring this minus half inside using logarithm rules, and we'll have the natural log of, let's see, 1 over the square root of u plus I times t, and then we'll have plus our constant c. But now let's take this expression for the natural log, or for z, and we'll set u equal to 0 to see what we get. So as we discussed over there, if we set u equal to 0, we end up with the natural log of the square root of pi over 4t, so that's cool. And then here we'll end up with the natural log of, well, 1 over the square root of I times t. So something like that. And then plus our constant c, which of course we're trying to get at that constant. Okay, so now let's move some things around. We'll have our constant c is the natural log of the square root of pi over 4 times t minus the natural log of 1 over I times t in a square root. Again, we can use log rules here to give us the natural log of the square root of I times the square root of pi over 4. The t disappears when we do this, subtraction turns into a quotient. Then next up, let's recall what the square root of I is, which I think we've calculated on the channel before, but it's like a really popular math YouTube problem, so you can probably find a derivation of that if you need to. The square root of I is indeed 1 plus I over the square root of 2. So putting that into here, we'll see that we in fact get the natural log of 1 plus I times the square root of pi over 8. Great, so that's because we can take this square root of 2 inside and turn that 4 to an 8. Okay, so that's our constant c, which we can take here and put right into this position. But let's do that with a clean board. So here's where we ended up on the last board. But let's recall that our real goal is this lowercase a and this lowercase b. So let's notice that the natural log of lowercase a plus I times lowercase b is in fact really just the limit as t goes to 0 from above and u goes to 1 of the natural log of z, given that z is capital A plus I times capital B. So if we let t approach 0, we'll end up with 1 over the square root of u, and then if we let u approach 1, we end up with the natural log of 1, which is 0. So under this limit right here, this term goes to 0, which is nice because we're just left with this constant. This natural log of 1 plus I times the square root of pi over 8. Okay, so now let's look at both sides of the equation. we have this natural log of a plus ib is this natural log right here. But that means that a plus ib is equal to the square root of pi over 8 plus I times the square root of pi over 8. But then extracting real and imaginary parts from both sides of the equation, we see that we get a equals b equals the square root of pi over 8, which that is the well-known value of these two Fresnel integrals. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.